maybe. All right, so in chapter 2 here, slide 12. We talked about some stuff there, right? So we talked about some electron configuration, I believe. And we also, again, talked about orbital diagram. We also talked about the periodic table. And obviously, you need to know different parts of the periodic table, groups, periods, special names of the groups, where metals, nonmetals, and metalloids are located. Then we're finishing up kind of talking about periodic trends, and we talked about a couple of them there. We talked about Z effective or effective nuclear charge. That again is the positive charge that those outer valence electrons or highest energy electrons feel as a result of what's known as shielding. So I think we looked at sort of lithium as an example. And again, lithium has a +3 overall charge in its nucleus, as it has a 1s2, 2s1 configuration, with it having one valence electron as it is in group number 1, which means it does have one valence electron. And what we talked about was kind of those lower energy electrons would actually shield the higher energy valence electron from the full brunt of the positive charge of the nucleus. So there is obviously an attraction between negatively charged electrons and the nucleus, which is ultimately positively charged. But the strength of that does increase with sort of the size of the charge. So those core electrons, which are these guys here that are closer to the nucleus, they are really right up front and going to feel the full sort of brunt of that +3 charge, and they're going to be held really, really tightly because of that. Now, on the other hand, as we talked about, you could actually calculate the actual effective nuclear charge that that valence electron, which is out here, is actually experiencing, and that is a result of those lower energy electrons actually shielding it. So they are sort of in the way of that outer electron sort of feeling the full sort of force of that +3 charge. So you could take something like the +3 charge from the nucleus minus the number of shielding electrons in this case, which are these guys, and instead of that +3 sort of attraction again to the nucleus, that outer electron is really only feeling a +1 attraction. So obviously it's still attracted, but it is not as attracted as much as those core electrons. And that's what I'll talk about in the next chapter, which is bonding. Again, it is why the valence electron is involved in bonding. It's not held as tightly. It can be released. It can be shared, as opposed to those core electrons, which are held too tightly to really sort of remove. The general trend in effective nuclear charge is for Z effective is as you go up and to the right, it increases, and as you go down to left, it decreases. And again, as you go kind of to the right on the periodic table, things have more protons as the atomic number kind of increases. So ultimately, they're kind of starting out at a more attractive sort of position. This is people on the left-hand side. Again, just at the case of how many protons they have, they're going to have a bigger positive charge to begin with, and that's going to bring things closer in just in general overall because of that larger positive charge. We also talked about ionization energy, and ionization energy is the energy required to remove an electron. In the gas phase. And there is a situation where electrons do come off, again, as we talked about when we talked about magnesium, I think, they do come off one at a time. So again, the first thing that would happen is this magnesium would lose one electron on the product side there. And that would be the first ionization energy required to do that. Then what would happen is this guy that has lost one electron would then dump off a second electron, and that is the second ionization energy, and obviously third electron, third ionization energy, and so forth. So the electrons, again, do come off one at a time. There's an ionization energy associated with each of those, and as we talked about, I think at the very end last time, it does get progressively harder every time you remove an electron to try to sort of remove the next electron. Again, because what happens when they do lose an electron is the overall electron density shrinks, right? So the overall size now of your ion that's positively charged is smaller than where it started with. So that's going to bring even those outer electrons now closer to that positive charge, and they're going to be held tighter, which requires more energy to do so. You lose the next one, same kind of thing happens. It kind of shrinks down a little bit more. And again, that's going to move everything make closer to the nucleus and held tighter. So the general trend in terms of first ionization energy to second to third to fourth, or however many electrons you want to take off, is it will start to increase. And what we saw was at some point, like in the case of magnesium, you will hit those core electrons. So after magnesium loses 2 of its valence electrons, you're now into the core electrons. And as you remember from that table, there was a really big jump in terms of energy required to kind of remove those electrons. And under normal conditions, that's not going to really happen. It's not really energy efficient to do so. And that's why, for example, something like magnesium will only dump off is 2 electrons, basically, and has really a fixed positive charge because of that. Same thing with something like sodium as well. Again, as you get into those core electrons, it gets a lot harder. The general trend for first ionization energy is as you go up and to the right, it increases, and as you go down and to the left, it decreases in terms of ionization energy. Any questions on that stuff there? All right, then here is that table we're looking at, I think, towards the end there. And again, here's that magnesium. And you can see a pretty big jump as we try to get into those core electrons. We see an even bigger effect, for example, here with aluminum, even bigger effect in terms of jumping. And in general, as you go from like the first electron to the second to the third and so forth, you can see, again, it gets requires more and more energy to remove it. And it means it's harder and harder, obviously, to remove it as you do so. So in general, as we go across a period from left to right, as we talked about, it does increase. And again, electrons are added to the same principal quantum number, so they're not shielded by those. So the increase in nuclear charge is caused by really the added protons. And again, because as we go to the right, we have that greater positive charge in the nucleus, going to hold even those outer electrons closer to the nucleus. And that means they're going to be held tighter and take a lot more energy to sort of remove them. And as we just talked about there in general, as we go down a group, we see ionization energy decrease. And again, the electrons that are being removed are on average farther away from the nucleus. Again, as you kind of go left and down, you're also getting into a situation where you just have a lot more electrons. So just by that process, they're going to be further away from the nucleus. It's going to be a little bit bigger. They're not going to be held as tighter or tightly, and it's going to be a little bit easier to kind of remove those guys as you go that way. All right. So we don't have to worry too much about this, but again, when we look at that sort of graph that we just kind of scooted by there, it's not a linear relationship. And again, we are talking about electrons near each other, and they're all negatively charged. So we do have some electron-electron repulsion sort of happening. So we don't get this nice linear relationship because, you know, they don't really want to be near each other. All right, so which one would require more energy to remove an electron? Should it be sodium or chlorine? It should be in this case. Should be chlorine, right? Chlorine and sodium are in the same period, right? We got sodium here, chlorine over here, chlorine way to the right of sodium in the same period, which means it has a higher ionization energy. It also has a lot more protons. So again, those outer electrons are going to be closer to begin with to the nucleus than what we have with sodium, which only has 11 protons in that case. Which atom would require more energy to remove an electron? So take a moment there and think about it. Should it be lithium or cesium? So in this situation, we are comparing two in the same group. So again, ionization energy decreases as you go down the group. So here, lithium would be harder to remove an electron, right? And again, if you just think about lithium, only's got 3 electrons, right? And again, 3 protons. So as you go down the group there, CCM is like shooting at 55, right? So just in general has a lot more electrons just by that principle. It's got to be further away from the nucleus as it'll be on different energy levels and again, not held as tightly. Which has the larger second ionization energy. So take a second there, lithium or beryllium, which one would have the higher second ionization energy? So in this case, we should go with lithium. Yeah. So lithium should have the higher. Whoops, wrong way. Let's go the right way. Lithium should have the higher second ionization energy. Why is that? Well, if we look at lithium, it has how many valence electrons? It's group number 1, which means it has 1 valence electron, which is that electron there. Beryllium is group number 2, which means it has 2 valence electrons. Remember, the group number equals the number of valence electrons. So when we talk about the second ionization energy, that is the removal of the second electron, right? Now, when we get to lithium, after you remove the first valence electron, you are now into the core electrons, which are good luck trying to remove those. That's going to take a lot of energy to do so. When you remove the first electron on beryllium, you still got 1 more valence electron to remove, which is going to be harder than the first one, but much easier than trying to remove a core electron in this case. So because beryllium has actually 2 valence electrons, you're still trying to remove a valence electron when you do the second one with beryllium, which should be easier than trying to remove a core electron in lithium. Any questions out there? All right, the next trend we're going to talk about is electron affinity. And electron affinity is much like the name implies. If you have an affinity for something, you like it. And when we talk about electron affinity, that is different, by the way, than electronegativity, which we'll talk about in just a second. This is actually the energy change that occurs when an atom gains an electron. And when we think about atoms gaining electrons, they become anions, basically, in that case. So when we think about electron affinity, we kind of think about anion and anion formation, negatively charged ions. When we think about ionization energy, like we talked about earlier, that's somebody losing electrons, so that's cation formation, positively charged ions, when we think about that. Whoops. And in general, electron affinity increases as you go up and to the left on the periodic table and decreases. It's actually not a perfect trend. If you actually look in group 7, as you go up group 7, it starts to increase and then it kind of decreases from chlorine to fluorine. So it's not a perfect trend, but in general, the trend for electron affinity is as you go to the right there, those guys tend to gain electrons. And as you go left and down, they tend not to gain electrons. They're not really looking to sort of gain those electrons. As I mentioned a second ago, this is different than electronegativity. And if we talk about electronegativity, which is another sort of important trend, which is actually in chapter 3, that is the ability of an atom to attract electrons towards itself. And this is the only thing you need to know for chapter 3 for the first exam, and then we'll obviously do more of it for the second exam, but you need to know what electronegativity is and the general trend. The general trend in electronegativity, when you look on the periodic table, is it increases as you go up and to the right. Actually, fluorine is the most electronegative element you could have. and it decreases as you go down. And that makes sense if you think about electron affinity. We have electronegativity increasing as you go up and to the right, which means those guys like to bring electrons towards themselves, which means it's a pretty good chance they're going to then gain an electron by doing so. And that's why we see an increase in electron affinity as we go to the right, because they're bringing those electrons close to themselves. Good chance they're going to gain them. And then we would see that electron affinity difference happening. Any questions on that there? The last sort of trend here we're going to talk about is atomic radius. And in general, as you go to the right on the periodic table, size gets smaller. And that is what we were talking about. Up and to the right, size does get smaller. Again, you have a greater nuclear charge. You also have an increase in that effective nuclear charge because of that. And what that means is, again, even the outer electrons are going to be brought in closer to the nucleus because of the greater positive charge in the nucleus. And it does decrease. I'm sorry, the size gets larger as you go left and down on the periodic table. Again, you have two things happening in that situation. You have a smaller effective nuclear charge, so things on the left, those outer electrons don't feel as much of a pull towards the nucleus, so they just kind of hang out a little further away. They're not attracted as close to the nucleus. And as you go down as well, you just have a lot more electrons piled in there at different energy levels. And again, because they're not going to feel that big effective nuclear charge, they're not going to pull themselves closer to the nucleus. So overall size of the atom gets larger as you go left and down, as opposed to up and to the right, where that effective nuclear charge gets really big or bigger, and also will bring those outer electrons closer in. So how does all these things sort of tie together? As you can see here, as you go across there, up to the periodic table and up and right, size gets smaller and obviously it gets larger over here. This is also why something big like this, where the electrons are out further away from the nucleus, not a lot of ionization energy needed to remove those electrons. Over here, very small size, electrons are very closer to the nucleus, again, going to be held lighter as a result of that. So how do all these things sort of play together? Well, they play together like so, I think. We think about the periodic table and all those sort of trends we talked about. The effective nuclear charge increases as you go up and to the right, decreases as you go down. With that, ionization energy increases as you go up and to the right, decreases as you go down. The electron affinity increases as you go up and to the right, decreases as you go down. The electronegativity increases as you go up and to the right and decreases as you go down. And size, right, actually decreases as you go up and to the right and increases as you go down. By the way, when we do gain electrons, the ion is actually larger than the neutral guy, right? Because instead of losing electron density, it actually gains electron density. So the negatively charged ion is going to be larger than the neutral guy because it's gaining those electrons into its electron cloud. So what does all these things sort of tell us? It obviously tells us what we kind of know. As you go on the periodic table, upper right of the periodic table, we have all kinds of elements that have a large effective nuclear charge, which means even the outer electrons are going to be closer. That will make the overall size of the atom smaller because they're coming in. They have very high ionization energy because those outer electrons are closer to the nucleus. They want to hold on to their electrons, so it takes a lot of energy to try to remove them. They both like to bring electrons towards themselves with a high electronegativity and gain electrons with a high electron affinity. So that tells us everybody up here in our non-metal region of the periodic table typically likes to gain electrons, right? And that is why when we think about anions, they are negatively charged and they typically are nonmetals. And that is opposite of what we see on the lower left of the periodic table. On the lower left of the periodic table, all those guys have really the opposite sort of trends. They have a low effective nuclear charge, which, as I mentioned a second ago, pretty much will not draw in those outer electrons really close to the atom. They have a lot more electrons as well, which means the overall size is going to be larger. It doesn't take a lot of convincing for them to lose electrons. They have a very low ionization energy, and they could care less about electronegativity and electron affinity. They're not looking to gain electrons or bring electrons towards themselves. And that's why when we think about metals, they typically are the ones that will lose electrons and become positively charged, why these guys would become negatively charged. And that's how all those sort of trends sort of work together. That's also why, as we saw in a couple of those experiments, most reactive nonmetal is upper right of the periodic table, because they have all the properties of, if you give me an electron near me, I'm going to take it, right? Which makes it pretty reactive. And lower left of the periodic table is where we see our most reactive metal, because they have properties of, just go ahead and take my electron. I'm not going to fight you. You can take it super easy, and it's going to be released pretty easy. And that's going to make it really, really reactive, right? And that's why we saw those trends of non-metal reactivity towards the upper right, metal reactivity towards down to the left on the periodic table. Because of these periodic trends, this is why we see that. Any questions on that there? All right, so which one should be the larger atom here, sodium or chlorine? The larger atom should be sodium, yeah. Again, it's in the same period. Sodium is further to the left, which means it has all those trends. It's going to allow it really not to hold all of its electrons super close to the nucleus, right? So it's going to have a little bit less of a pull towards it. Lithium and cesium here. The larger atom, again, they're in the same group, so size increases as we go down. So here it should be cesium is our champion there. All right, so take a moment on each of these. We want to know which one is larger, the hydrogen 1s orbital or the lithium 1s orbital, and which one is lower in energy, the hydrogen 1s orbital or the lithium 1s orbital. So the larger one in this case should be the hydrogen here, right? And the idea is, if this is our 1s orbital just kind of floating around there, I suppose, the attraction to our hydrogen is only a +1 attraction, right? But our attraction to lithium is a +3, because it has 3 protons in its nucleus. And the larger the attraction of that positive charge is going to bring that 1s orbital closer. And overall, the size of this guy is going to be smaller than it would be, because this 1s orbital is not coming in as close. And so overall, it's going to be bigger. So our hydrogen 1s orbital should be the larger one because of that, because again, that +3 charge in lithium should bring that s orbital closer in, giving it an overall size much smaller. Now, that also plays into really the second question, which is which one should be lower in energy? And the lower in energy should be the lithium in this case, really for the same reason. Because of that +3 charge, it's going to drag this 1s orbital closer to the nucleus. And by it being closer to the nucleus, it's going to be lower in energy, right? And again, the 1s orbital in hydrogen is not going to be drawn in as close, so it'll be a little bit higher in terms of energy. Any questions on either of those there? All right, so I think this is the actual order, so we'll just talk about it. Arrange each of these in terms of increasing ionization energy and atomic size. And if we look on the periodic table, this is sort of where we find all these guys. This is sort of the arrangement. And when we talk about ionization energy, again, it increases up and to the right, decreases down. So in terms of smallest ionization energy, it should be sulfur to oxygen to fluorine in terms of being low to highest ionization energy in that pathway. In terms of atomic size, it decreases as we go up and to the right and increases as we go down to the left. So the opposite here, we're going to go from smallest, which would be fluorine, down to sulfur, which would be the largest in this case. Any questions on that there? All right. I believe that should wrap up this chapter, I think. All right, some final thoughts that we sort of talked about. Again, the number and type of valence electrons determines this chemistry. Electron configuration can be determined from the periodic table. As we talked about, you do want to be careful if you're trying to count it off. There's some places like where the D's and the F sort of incorporate in. So again, if you follow that zigzag thing, you're probably in better shape. All right, there we go. Super final thought there. All right, that is chapter 2. Reminder that what we just finished is pretty much the last stuff that will be on our exam, which, if I am not mistaken, is 1 week from today. I believe it is scheduled. Yeah, sounds like a winner. And again, it's on chapter 1 and chapter 2. And again, the only thing that you need to know for exam 1 from chapter 3 is electronegativity. You need to know basically what it is. You need to know the periodic trend of it. And obviously in this chapter, we'll go much greater into electronegativity. All that stuff will be for the next exam. But for exam 1, you do need to know electronegativity, what it is, and the periodic trend. And that's pretty much all you need to know out of chapter 3. Yeah. All right, so this is now, I guess, exam 2 material here, chapter 3. So we're going to talk a little bit about bonding here in chapter 3, and then we will talk more about bonding in chapter 4. And then we'll come back, I think, to chapter 3 and hit the last section or so and talk about naming, everybody else's favorite thing. So a lot of everybody's favorite thing coming up here in these chapters. All right, so Lewis dot symbols, right, are ways that we represent bonding. And I believe we talked about in the last chapter, but just a reminder, right, when we talk about bonding, it's all about those valence electrons, which are those highest energy electrons. And remember that you could either write the electron configuration to figure out how many valence electrons somebody has, but nobody wants to do that. So the number of valence electrons does equal the group number on the periodic table. So that obviously is a much faster way to probably figure out the number of valence electrons that you show. So a Lewis dot symbol, which is also sometimes just more generically called these days an electron dot symbol, is basically a symbol that represents the element and 1 dot for each valence electron that it has. And in a Lewis dot symbol, we only show the valence electrons. It is important to remember that they do have obviously those other core electrons, but only in bonding do we show those valence electrons. So a Lewis dot symbol, as I mentioned, does basically consist of the element symbol. There's really no fast rule on that other than no more than 2 dots per side. So, you just can't go more than 2 dots per side. And if there's 4 sides to a symbol there, that is 8 electron. And as you might know, 8 is quite an important number in bonding. It is pretty much what everybody is trying to achieve. And by the way, who has 8 valence electrons on the periodic table? The noble gases. Yeah. So as we talked about when we did electron configuration, and as we'll see here in this chapter, is the purpose really of all bonding, ionic bonding, covalent bonding, is for everybody to achieve the same electron configuration, be isoelectronic with a noble gas, which will make a really stable situation. I would say sometimes people just go one at a time and then pair them up. But again, as long as you don't do more than 2 per side, you should be good. I made this one day when I was bored. I really should get a hobby, but here are some Lewis dot symbols for all these things. We typically don't do too as much bonding with what's there in the transition metal region. But again, we got our 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. One exception is helium, right? Helium only has 2 total electrons, so it has 2 valence electrons. And that's really important because there is only one element that comes before helium on the periodic table. And who is that? As hydrogen, which means hydrogen's journey is just to helium. And when hydrogen is involved in bonding, only 2 electrons for hydrogen. Super important, yes. So you don't like triple bond hydrogen and then for good measure triple bond it and put dots all the way around it and it ends up with like 12 electrons or 42 electrons, however many dots you put on there. So hydrogen only needs to get to 2. Pretty much everybody else on the periodic table's got to get to these guys, which are 8. But hydrogen definitely only 2. Should never go over 2. Basically, hydrogen should only look like pretty much this. And that's it. Nothing else on it. It should be pretty bare there. So let's first talk about what Lewis dot symbols could help us understand. And we're going to talk about both of these here. We're going to first talk about ionic compounds. And what makes up an ionic compound is always really this combination. It is always a metal and a non-metal together. So when you see a metal and a non-metal that is coming together, that should just scream to you ionic compound. And what's going to happen is based on those periodic trends that we just talked about, our metal is going to be the one that's going to basically get rid of electrons over to our non-metal. And that is the result where our metal then becomes charged and has a charge and become positively charged as it loses electrons. And that's when our non-metal will actually become negatively charged. And that attraction is actually what holds together an ionic compound. There's absolutely no sharing of electrons in an ionic bond. It is only really electrostatic attraction, which is a fancy way of saying the positive negative attraction is what holds that together. The charges is actually what holds that together. And that's different as we will see in a covalent compound that has covalent bonds. In covalent bonding, it's all about 2 nonmetals coming together. And if you just think about the location of nonmetals on the periodic table, they're all sitting in the same location, which means if you think about those periodic trends we just talked about, they all have similar periodic trends, which means neither one of the nonmetals is going to be willing to lose its electrons. Neither one of them want to give it up, right? You don't have that problem in a ionic compound because metals are like, just go ahead and take them. I don't really care, right? I care less. You could take them, no problem. But when we get 2 nonmetals together, what happens is neither one wants to get rid of their electrons. So the best that they could kind of agree upon is we're not going to lose our electrons, but instead we'll just kind of share them. Yeah, so we'll share them rather than lose them. And you get actually sharing of electrons here, as we'll talk about. Here, there is no sharing of electrons. Yeah. And in general, those periodic trends, as we just talked about, are really important for understanding what's going to happen and what type of bond that's going to happen. So typically speaking, if you got somebody on the left-hand side of the periodic table, which is the metal, has all those characteristics that want to get rid of their electrons, hooks up with somebody on the right-hand side of the periodic table that has all the characteristics of, I want to keep my electrons and gain electrons. That's why we see that electron getting transferred. Again, if everybody's hanging out there on the right-hand side of the periodic table in the non-metal region, neither one of them is going to want to lose their electrons, so they're just going to agree to share. Now, the general rule tells us that typically cations are found there on our metal side. Halogens, oxygens, and all those guys is where we're going to find our negatively charged guys. I think we've talked about it previously, but again, a reminder that nothing on the periodic table has a charge until sort of they come together here in an ionic compound and form an ionic bond. So let's take a look at an example like lithium fluoride. Lithium is a metal. Fluoride, which is fluorine, is a nonmetal. So that combination tells me I am looking at an ionic bond that's going to happen. So if I take a look at what's happening here with our Lewis dot symbols, I could use lithium here, and lithium is group number 1 on the periodic table, which means it has 1 valence electron. It's going to hook up there with fluorine, which is group 7 on the periodic table, which means it has 7 valence electrons. If we lay up ourselves here a little electron configuration, 1s2, 2s1, right there is its 1 valence electron that you see in the picture. And fluorine there, which is 9, 1s2, 2s2, 2p, Was that 5, I think. And right here, all those on the second energy level are 7 valence electrons that we see in fluorine. So again, we have a metal that pretty much will give away its electrons if you just ask nicely. We have fluorine, which will not give away its electrons, but definitely will take somebody's electrons. So when these two guys get together, because of those periodic trends, Mr. Electron here is going to send himself over there to the fluorine. The result of this is our lithium has now lost the valence electron and will now become positively charged because it's now short an electron. The fluorine here will pick up that electron right there. And when it does, it will now become negatively charged. And we have now created two ions which are attracted to each other through the electrostatic attraction are the positive and negative charges. Once again, there is no sharing of electrons here. And that is why when we draw a Lewis symbols for ionic bonding, we do need to include the charge to indicate that there is no sharing of electrons here. There is no lines being drawn here because there's no bonds actually being made here. And we oftentimes will either put one of them like I did there in brackets or both of them in brackets. But again, just to indicate that. First off, any questions on that there? So what happens to our lithium? Well, our lithium basically sent this electron here over to here. The result of that is now lithium with a +1 charge no longer has that. And it has an electron configuration of 1s2. And if we look on the periodic table, the one with 2 electrons is helium, which is a noble gas. So here, lithium with a +1 charge is able to achieve the same electron configuration as a noble gas by giving away its electron. Since fluorine has a spot for it right about there, when it gains that electron, it becomes 1s2, 2s2, 2p6. That is 6 and 2 and 2. All the top numbers is 10. And if you look on the periodic table, number 10 there is neon, also a noble gas. And again, that is ultimately the purpose of bonding. Each of these, by transferring electrons, gaining and losing electrons, both of these guys on the right-hand side here, when they form their ions and their ionic bond, are able to achieve noble gas configuration in terms of their electrons. Again, they're isoelectronic with those noble gases, and that makes a really, really stable bond. Any questions out there? All right, so let's take a look at maybe another example here. That's basically what I just wrote. Very good. So as I mentioned before, that bond between the lithium ion and the fluoride ion is again held together by the electrostatic attraction. Once again, there is absolutely no sharing of electrons happening in this situation. They're just held together by the attraction force. Much like we were talking about the positive and negative attraction, larger positive charge, larger negative charge is going to be held tighter than something with a smaller, so +1, -1 sort of charge. So let's take a look at calcium chloride or calcium oxide. Calcium, which is group number 2 on the periodic table, would have 2 electrons. And once again here, we would have an electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, or if you want to shorten it there, argon 4s2, these being the 2 valence electrons that we see in calcium. We hook that guy up there with oxygen, which is group number 6, which means it's got 6 valence electrons. I guess I could have done it the other way. Actually, I will. I can get rid of one of those electrons on the bottom so I don't have to draw such a long arrow. All right, let's get rid of that guy there. Perfect. All right, so if we look at electron configuration here for oxygen, 1s2, 2s2, 2p4 in this case. This being the 6 valence electrons that oxygen has in this case. So same situation here. We got somebody on the left-hand side hooking up with somebody on the upper right. That oxygen is going to really bring those electrons towards itself. Calcium is not going to put up much of a fight. And this electron is going to send itself over. This electron is going to send itself over. And the result of that is calcium here lost not one, but two electrons and will become positively charged. The oxygen, which has room for those two right about there, and that p subshell that could hold 6 electrons, so it's got room for those 2 incoming electrons, will gain those 2 electrons. And the result of that is because it gained 2 electrons, it now will have a -2 charge. And once again here, what's holding that together is the charges, the positive and negative attraction between those two. Now, same thing in terms of what's happening when calcium loses those 2 electrons. It will end up with the same electron configuration as argon in this case. 1s2, 2s2, 2p6, 3s2, 3p6, or 18 electrons. Oxygen, by putting those 2 electrons in, will end up at 1s2, 2s2, 2p6, or again, neon's configuration. So once again here, both of those elements are able to achieve noble gas configuration by the transfer, in this case, actually of 2 electrons. Calcium needs to get rid of 2 electrons, right? Because it's the only way it could get all the way back to our noble gas. So as we talked about when we're doing electron configuration, when our representative metals lose electrons, they move backwards on the periodic table to the noble gas that comes before them. And when our nonmetals gain electrons, they go forward on the periodic table to the noble gas that comes after them. So if you look on the periodic table, neon is after oxygen, argon is before calcium on the periodic table. So again, it backs up on it. Any questions on that? Now, what happens if we kind of put together maybe both of those things that we just talked about? And I'll do it here. Next slide. Let me see. Yeah, I'll do it on this slide actually. So let's say we put together, though, calcium, which has obviously the 2 valence electrons hanging out at argon 4s2. And we put it together with fluorine, which is again group 7, like we saw earlier, has 1s2, 2s2, 2p5. So in this particular case, what's going to happen is calcium is going to get rid of its electrons because it wants to do so. So when I send this electron over to my fluorine, can that fluorine at this point take any more electrons? It cannot, right? Because now it has 8 around it, so it is full. The problem with that, though, again, if you look on the periodic table, if calcium only lays up 1 electron and gets rid of it, it's only going to move backwards to potassium. And it doesn't have the same ring as a noble gas, right? That's an alkali metal. So it's not going to be really happy that way. So in this particular case, calcium needs another place to dump its electrons. So it actually would need not 1 fluorine in this case, but it would actually need a second fluorine to give it a spot to dump its second electron. Now calcium, by giving away 1 electron to each of those fluorines, will achieve calcium with a +2 charge, which is his ultimate goal. Each of those individual fluorines will pick up only 1 electron, and because of that will become negatively 1 charged. And really, you could draw it on this side, but I didn't have a lot of room. What happens now in this case is calcium able to get rid of both of those. So the calcium here now achieves argon's electron configuration. This fluorine here gained only 1 electron, which is all it needed to go forward on the periodic table to achieve neon's configuration. This fluorine here gained 1 electron, which it only needed to go forward 1 spot to get to neon's configuration. So in this case, all 3 of these guys basically achieve noble gas configuration by gaining and losing electrons. This is why, for example, if you remember when you did naming or writing formulas for anything that's ionic, and you have something with a +2 charge and a -1 charge, you're supposed to put those guys together so the overall charge equals 0, right? And that is why you need this guy. so that you get the proper formula of this. And the real reason is actually the bonding reason here. Without that extra fluorine here to get it to 0 in the simplest way possible, calcium would never live to get to that noble gas configuration. And that's really the reason why they tell you when you're doing nomenclature and you write a formula for an ionic compound, the overall charge has to equal 0. It's really for this bonding situation that they need to gain enough electrons. And when you do that and you put that formula technically together in the simplest way to get to 0, you're basically allowing everybody in that formula to hit noble gas configuration, become really, really stable. So that's really the kind of the purpose why we do those things. Any questions on ionic bonding here? All right, so that's ionic bonding. Then let's talk about what happens with covalent bonding, which clearly my things are really messed up here, so I'll just redraw them. So covalent bonding is definitely different than ionic bonding. And the first major difference is it involves two nonmetals, right? So if you got two nonmetals together, you're going to have some type of covalent bonding, and you're going to have some type of sharing of electrons here. And again, unlike in an ionic compound where you have a metal and a nonmetal and no sharing of electrons, here you do have sharing of electrons. You could share equally, as we'll talk about, or it can be unequal sharing of electrons. But there is some aspect of sharing that's happening in a covalent bond. So Gilbert Lewis, hence Lewis structures, Lewis dot symbols, developed the idea of bonding as this. For example, you have hydrogen that has one valence electron. You got hydrogen that has one and only one valence electron. And again, in this case, they obviously have the same sort of periodic trends. So neither one of them is going to give up its electron. So what's going to happen in this situation is they're going to decide, all right, we'll just kind of share those electrons and make a covalent bond where we share electrons. And again, what happens in this situation is those two electrons in the middle count for the hydrogen on the left, and those two electrons in the middle account for the hydrogen on the right. So ultimately, by sharing electrons here, each of the hydrogens end up with two electrons. And as we talked about, that's really good because, again, hydrogen should only get to 2, which is what it needs. So it creates a nice stable bond. You could show that as dots. You could also show that as a line. And one line represents a single bond. And that basically is the sharing of a pair of electrons. As we'll see later, 2 lines is a double bond. And that is the sharing of 4 total electrons or 2 electron pairs. And a 3-pack of lines there is our triple bond. And that is the sharing of 6 total electrons or 3 electron pairs. You could show this sort of bond here as either dots or lines, whichever one you like. Most people will use lines to represent a bond formed, and people will kind of use the dots for just non-bonding electrons or electrons that are not involved in bonds. Now, in a covalent bond, each of those electrons that are being shared between the two atoms, they're basically both of those electrons are attracted to each of the nucleuses. And that's sort of what holds it all together. You got electron density kind of in the middle of the two, and it's kind of attracted to the positive charge of this guy's nucleus, but it's also attracted to the positive charge of the other guy's nucleus. And it kind of just holds everything together through those sharing of electrons. Let's take a look at another example here. We have fluorine, which has an electron configuration of 1s2, 2s2, 2p5. As we talked about previously, it will have 7 valence electrons. In this situation, once again, it is fluorine on both sides, identical sort of periodic trends. So they're just going to agree to share those electrons. And the result of that is you will get a bond formed between the two fluorines that you can represent like that, or once again, the actual bond between the two atoms can be represented with a line. So if you see a line, it does represent 2 electrons or a pair of electrons. And once again here, if we take a look at what's happening through the sharing of electrons, those 2 electrons count for the fluorine on the left, which means ultimately it has 8 electrons. And those 2 electrons count for the fluorine on the right, which means it has 8 electrons. And once again, that moves everybody over there to the noble gases, which is group 8 on the periodic table. And again, the way that in a covalent bond situation, they're able to achieve sort of that noble gas configuration is through sharing of electrons. And that, again, is different than what we see in a ionic situation where we have a transfer of electrons that is occurring. Any questions on that there? Now, when we look at this, there are 2 different types of electrons that we see there. All the ones that are not involved in bonds, so all these dots, these are what are referred to, I would say, nowadays as non-bonding electrons. If you're old like me, you will call them lone pairs. So when I say lone pairs, it basically means non-bonding electrons. And there's also obviously a name for the one that's involved in the bond, which are these 2 electrons in this particular case right there. That also has a super creative name since it's involved in the bond. Those are known as bonding electrons. Yeah. So we have obviously bonding electrons, which are involved in a bond formation. And again, most of the time people will use a line to represent that. And we have lone pairs or non-bonding electrons, which are not involved in any bond formation. And you should use really dots for that, not lines. So use dots for that. So a Lewis structure, as I mentioned, does really only show covalent bonding and only shows really the valence electrons. Again, a reminder that it does have other electrons, those core electrons, each of these elements, but again, they are not involved in bonding and not shown in the actual structure. Take a look at a couple other examples like water, for example, here. Water, by sharing electrons, the oxygen is sharing electrons with the hydrogen, actually on both sides, allows it to reach that noble gas configuration of 8 electrons. And each of the hydrogens, by sharing one electron with the oxygen, also able to reach 2 electrons, which is what it needs. So again, that, as we talked about, is the goal. Once again, here, these guys here would be, whoops, coming into here. Those guys there would be bonding electrons. And obviously, these guys here would be non-bonding electrons. So that does bring us to the important rules of bonding, which we've basically been talking about. So officially speaking, the octet rule is essentially the bonding that we do. The octet rule basically says that except for hydrogen, everybody will continue to make bonds until it has 8 valence electrons around it. And again, the goal of that, as we've been talking about, gets us to the noble gas configuration. Obviously, our one exception there is hydrogen, which once again only needs to get to helium, should only have 2. And once again, that is pretty much what hydrogen should look like. Hydrogen should always be on the outside of the molecule, because if you put it in the middle, it's going to have way more than 2 electrons. So hydrogen should always just be hanging on the outside. Again, no dots around hydrogen, no double bonding hydrogen, no triple bonding hydrogen, unless you like the letter X. So you probably don't want that letter, right? So don't do any of those things. Although it is my kind of favorite when I see it sometimes on paper. Is like, I'm just gonna go all in just to make sure I don't miss anything here. So that gets like a double X, I think, just for that. Yeah. So don't do that. And once again, hydrogen. Yeah. All right. So we talked a little bit about this earlier here, but again, officially as well. Obviously, we have different types of bonds that we'll talk about in a little bit more detail in some next chapter as well. But again, single bonds is sometimes all you need to get yourself to the octet rule and to get everybody to 8. It's just a single bond will do it. As we see here with fluorine, it gets everybody to those 8 valence electrons. Sometimes it does require a double bond to do that. And sometimes, like here's CO2, it actually requires 2 double bonds there to do that on each side. And those 2 double bonds are necessary for carbon to get to 8. And as you can see here, each oxygen will still have 8 as well through that double bonding. So sometimes it does take one double bond to get you there, maybe 2 double bonds to get everybody into that octet rule. Obviously, as I mentioned before, single bond, one individual line are a pair of electrons. Double bond, 2 lines represents 2 pairs of electrons. And then sometimes it does take a triple bond to get yourself to the octet rule, and that happens, for example, with nitrogen. You actually need a triple bond here, and by each nitrogen sharing those 6 electrons in the middle, each of them will end up with 8 electrons, as that's 2 on the outside as well. And same thing here with ethylene, that has a triple bond between this. And again, for this carbon here, it has 1, 2, 3, 4 bonds, and each one has 2 electrons, so that's 8 electrons. And the same thing for this guy as well. Now, what happens in terms of how the electrons are going to be shared in this situation? Really, electronegativity is one of the big factors as to whether or not electrons will be shared equally or unequally. So since we just talked about in the last chapter, electronegativity, once again, is the ability of an atom to bring electrons towards itself. Now, as we just talked about, right there, fluorine is your most electronegative element. And again, it increases as you go up to the right and does decrease as you go down and to the left. So differences in electronegativity is a really big determining factor as to whether or not these two atoms will share those electrons equally or unequally. So for example, if we look at hydrogen, because they are both hydrogen atoms, they both have really the same electronegativity. So when the hydrogen on the left there and the hydrogen on the right pull on those electrons, you're essentially going to get pretty equal kind of pull in both directions on it. Essentially, you can think of it almost like a tug of war, right, with like a rope on each side and like a little flag in the middle, right? So if everybody pulls the rope equally, the flag's just going to kind of hang out there in the middle, not really go one way or the other. And this type of bond, where we have electrons being shared equally, is a special type of bond. It's referred to as a nonpolar covalent bond. And most people will just call it, in most cases, a nonpolar bond. To sort of imply that the electrons are going to be shared here. So if you have a nonpolar bond, what you basically have is essentially equal sharing of electrons. It is, for all intents purposes, because it's kind of equally being shared, you could think of it as like a neutral bond. There's no like positive side, there's no negative side, there's really no charge separation that's occurring because all the electrons are really being distributed and sort of shared equally between the two atoms. Now, what would happen if we didn't have, say, 2 hydrogens and we switched out one of the hydrogens for fluorine? So now when we do this and we have this bond in this case, when we look at the electronegativity of hydrogen versus fluorine, we know that fluorine is way more electronegative. It's actually the most electronegative element you could have. And what happens is when these two guys go to share electrons, it is actually the fluorine that's going to go bring the electrons closer to me. Yeah. So what's going to happen is the electrons are going to actually kind of flow in that bond shared between them a lot closer to the fluorine side. So if all my blue I just drew there is like the electron density, the electrons are going to be kind of hanging out on the fluorine side. Very little is going to be kind of still hanging out over there on the hydrogen side. The result of that is it's going to actually affect what's happening in terms of this bond. So if I had that occur, for example, would I expect the fluorine side to be more positive or more negative in this case? If all the electrons are hanging out on fluorine, it should be more negative, right? Electrons are negatively charged. So if all the electrons vacation over there by fluorine, you're going to end up with a more negative charge on the fluorine. That's going to create a partially negative charge on fluorine. That's a delta negative symbol, by the way. And that would make the hydrogen in this case partially positively charged. As the electrons are kind of moving away from the hydrogen is now becoming electron deficient and more positive, and the fluorine is kind of hanging on to some of those fluorine or electrons closer to fluorine becoming more negative in this case. You could also represent this with an arrow that you see a lot in bonding, and that arrow would point to the more electronegative side, and the back of the arrow will make like a positive sign by the more positive sign. That is what is sometimes referred to as a dipole arrow. And it basically represents what we see here, more positive and more negative. And once again, it always points to the more negative side here in this bond. So the end result of this is we do end up with these sort of partially negative charges and partially positive charges. Why are they only partially positive and partially negative charges and not like a full positive and a full negative charge? Why is that? Yeah, because there is still some aspect of sharing, right? So these electrons have not been transferred like we see in an ionic bond, where the one electron, the entire electron just clearly goes from one place to the next, and there's a transfer of electrons. The result of that in an ionic bond, when we get the transfer of electrons, is we're going to get full charges happening on our positive guy and our negative guy. Here, even though it's unequal sharing, there is some aspect of sharing. Hydrogen is hanging on, and he's not letting go of his electron in this case. He's still kind of hanging on to it. So if he wants to kind of like the tug of war situation, right? On this side, we have fluorine pulling, right? The flag's going this way. The poor hydrogen's on the tippy toes of the mud pile, right? Without getting pushed into the mud pile. So he's still hanging on to the rope at that point, or the electron in this point. So since there is still some aspect of sharing, that's why there are only partial positive and partial negative charges on this side here and this side here. This type of sharing of electrons, which is unequal sharing of electrons, is known as a polar covalent bond, or just a polar bond. And again, most people will just simply call it kind of a polar bond in this case. So a nonpolar bond, we have equal sharing of electrons. And that's why I said earlier, you could think of a nonpolar bond as like a neutral bond. Because the electrons are shared equally, there is no side like we see here that has more electrons hanging out than less electrons. So it's kind of like no charge on either side of that bond. And here we do end up with a polar bond. That's essentially what we just talked about, polar covalent bond. So once again, in a polar covalent bond, we have that unequal sharing of electrons. And again, it really is that electronegativity that helps us decide that. And when we look at electronegativity, sort of differences to decide how electrons are going to be shared or if they're going to be shared at all, that is what is sometimes referred to as looking at bond polarity. So bond polarity is sort of where we look at the difference in electronegativity values between the two atoms in a bond, and it tells us just simply between those two atoms how the electrons are going to be shared. Are they going to be shared equally, going to be shared unequally, and so forth. Once again, in some cases, as we'll talk about, it may actually tell you for the entire molecule. Like in this case, it does tell you for the entire molecule what's happening. But in other cases, it does not. And when you have more than one bond, you have to look at some other things that we'll talk about. So we can think about the three types of bonding that we talked about sort of this way. On one end of the extreme, we have an ionic bond, and that is always going to be between a metal and a non-metal. And that should kind of be almost a no-brainer on that. As soon as you see those two things, you should know it's ionic. You should know there's no sharing of electrons. You should know that there's going to be a transfer of electrons from the metal to the nonmetal. Going to result in a cation being formed from the metal and an anion being formed from the nonmetal. And again, we have no sharing of electrons. It is that electrostatic attraction that holds it together. A positive negative attraction between the ions. An example of that is any ionic compound you like to choose, like sodium chloride, for example, is an example of that. On the other end of the extreme, we have a nonpolar bond, or a nonpolar covalent bond, and that's between two nonmetals, which automatically tells you definitely there is sharing of electrons. And that sharing is going to be equal sharing of electrons. An example of that could be either one, like the H2, the F2 that we were looking at. Those are all examples of that. By the way, we will see shortly that it doesn't necessarily have to be two of the same element to have a nonpolar bond. It is possible to have two different elements that actually will share electrons equally with one another. And sort of in the middle of those two types of bonding is our polar bond, or our polar covalent bond. Also covalent bond, also between two nonmetals, also sharing of electrons. Here it's going to be unequal sharing of electrons, which gives us our partially negative, partially positive side. And obviously our HF is here. So again, on one end of the extreme over here, you have nobody sharing electrons. We're going to get complete transfer of electrons from one place to the next. On the other end of the extreme, you have perfectly equal, if you want to think about it that way, sharing of electrons between two atoms. And in the middle, you have no transfer of electrons, but not perfectly equal sharing of electrons. So you have unequal sharing of electrons, but it's not so unequal that those electrons actually jump from one place to the next. They're still hanging on, still holding on to those electrons. Any questions on the differences between those types of bonds? So as I mentioned before, it really is the electronegativity that is really the overwhelming thing that we look at in terms of bond polarity. And electronegativity, as we've been talking about, again, is the ability of an atom to bring electrons towards itself. It is based on electron affinity and ionization energy. So again, fluorine has a high electron affinity, likes to gain electrons, and a high ionization energy, doesn't like to lose electrons, so it has high electronegativity. It's like, I'm keeping my electrons and I would like to take yours. Sodium, which is a metal on the left-hand side of the periodic table, has low electron affinity, not looking to gain electrons, doesn't typically gain electrons, and has low ionization energy. Doesn't take, again, a lot of convincing to get them to lose its electrons. So how do we know if we actually have a polar bond versus a non-polar bond? We can look at the electronegativity values, and a guy by the name of Linus Pauling came up with a sort of scale for electronegativity. This is the Pauling scale. It runs from 0 to 4. 4 is the most electronegative. 0, not so much, yeah. Not so much electronegativity. So how do you use this? We calculate what is known as the change in electronegativity values. So it is basically a table, and it would be provided for you, the numbers. And you would go to that table, you would find the two elements that are involved in the bond. And frankly, all you have to do is subtract the numbers. And you can subtract the larger number from the smaller, so you get a positive number all the time. And if you subtract the numbers when you do that, and you get anywhere from 0 to 0.4, that is considered a nonpolar bond, and you would expect equal sharing of electrons here. If you get above 0.4, which is essentially 0.5, to below 2, that is going to result in a polar covalent bond, so unequal sharing of electrons. And typically speaking, if you are above 2, not in all cases, but in a lot of cases, you will end up with an ionic bond, a transfer of electrons. Now, if you end up with, for example, a difference in electronegativity that is 0, some books and some people will call a difference in electronegativity value of 0 a pure covalent bond. And that is a fancy way, covalent bond. That's just a fancy way of saying that's like as perfect equal sharing as you could get. So for example, if we did hydrogen, H2, whatever hydrogen's electronegativity value is, which by the way is like 2.1, if you go to the table, I think 2.1 sounds good. And if you did the difference in electronegativity for hydrogen and hydrogen, 2.1, 2.1, that is going to end up with 2.1 minus 2.1. That's 0. That's definitely going to be a nonpolar bond, and is sometimes classified as a pure covalent bond because that's like perfect equal sharing of electrons. So a pure covalent bond is still a nonpolar bond. It's just sometimes people will call it that because it's kind of perfect equal sharing of electrons. Any questions on that there? So just to show you a table, and we'll do more next time, but this is a negativity table, and as you can see, as you go up and to the right, we increase there to fluorine of 4. As you go kind of down to left, we got like 0.7 happening there with a less electronegativity. So again, you would go to that table. I did it right there, 2.1 for hydrogen, so that's not bad. So you find those two values, and again, just subtract them, and you could use that sort of cutoff that we have here as a determination of what type of bond you would expect. To be honest with you, I personally would only use probably